Oh boy, that's really bright. How's everybody doing? Good? Awesome. So let's play a game. Every time I say blockchain, you take a drink, OK? I think they're serving alcohol somewhere. So my name is Greg Slepak. These are some of the projects that I've worked on. That's my contact info. And I'm here to talk about the DCS theorem. Once upon a time, there was a blockchain. Now, this blockchain, the people called it Bitcoin. And it was a young blockchain. It was a growing blockchain. In fact, it had some growing pains. The block size debate brings back memories. How many of you have not heard of the block size debate? OK, no hands went up. That's good. So what was this all about? We had one side. Well, there was a problem. It started with a problem. As mentioned, Bitcoin was growing, and blocks were filling up with transactions. And there was only 1 megabyte in every block for those transactions to go into. And so once those blocks started getting full, transaction fees were rising, and there was a backlog accruing of transactions. So this was upsetting a lot of people. And so there was a debate about how to solve this scalability problem. And one side wanted to use this simple solution of just increasing the block size. And another side said no, they didn't want to do it that way. So one of the analogies that I ran across while reading about how the block size debate was being portrayed in the media was this one that used highways. And so the idea, the analogy was that you have a road, and it can get full with cars. And the more cars there are, the more traffic there is, and so everything goes slower, and you have to wait in line, and you might even have to pay a toll to get on the road. And so the proposed solution from the big block side was that, well, we can just add more lanes. This would be equivalent to increasing the block size. And the opposing side said that this would be unwieldy. This was how it was portrayed. That it would be kind of like this, trying to add 10 lanes, and it just wouldn't work. So this isn't really quite correct. Sticking with this analogy, a better analogy would be like there's a bunch of computers out there that are processing traffic. And this represents the global decentralized Bitcoin network of full nodes and miners. And those who were opposed to raising the block size were saying that this network is important because it represents all of the value behind Bitcoin, which is the fact that it's a decentralized consensus network. And so they were saying that the choice was this. If you raise the block size, not all of the computers out there are going to be able to handle that additional traffic, and they'll start dropping off. And in the end, we would end up with a small number of very powerful computers controlling the network. Or as Andrea Devers, the OK Turtles Foundation, where I work, puts it, it's important that all lappies can participate in the network, not just the big lappies. So welcome to the DCS theorem, which was born out of my desire to kind of put an end to the block size debate. And it's a triangle. It refers to a triangle relationship similar to other triangles you might have heard of, like easy, fast, cheap, pick two. It's the same kind of deal, except instead of easy, fast, cheap, we've got decentralization, consensus, and scale. So in the paper, which you can read if you're interested at okturtles.org/DCS, we have these very mathematical definitions of the terms, but I'll just give you a very layman's definition. Consensus just means that in some system, there's a group of people or computers that are voting on something. So when you hear consensus, think voting. Oops. Scale means that this system is able of competing with any other similar system that's trying to do the same thing in terms of the number of users that it's servicing. So in other words, it means that Bitcoin can compete with PayPal in terms of the amount of transactions that it processes. And decentralized means that the system doesn't have a single point of failure, which just means that if you can look at the system, what it's made of, and try and find in it, some little component, something to, to poke, that you're not going to take the system down by poking that one small part of it. Or in other words, there's no boss who is able to tell the system what to do. Now let's go back to the triangle and look at some examples. On the left edge of the triangle, we have systems that use consensus and scale. And here we have all of our traditional, well-known Silicon Valley companies. And why do I say that a company like Facebook or Slack or Twitter uses consensus? Well, it's because they run massive data centers with server farms with lots of computers that are networked together that have to come to agreement about the state of their database. So these systems actually do use consensus. But you'll notice we're missing one of the edges or the corners. These are not decentralized systems. At the bottom, we have new systems that have been recently developed, like Bitcoin and Ethereum. These are decentralized consensus systems, and unless you've been living under a rock, you might have noticed that they don't scale very well. And on the right, we have systems that are also decentralized, but they don't use consensus. And so they can scale really well because of that. The internet itself is an example of that. So TCP/IP, or BitTorrent, or recently, more relevant to this conference, the Lightning Network. So let's talk about decentralized consensus systems, like Bitcoin. Let's imagine that this set of circles represents Bitcoin. The big red circle represents all of the users of Bitcoin who are using the service that Bitcoin is providing, the payment service. And the green circle is the subset of users who are actually participating in the consensus process. So this would be the miners, mostly, and to another lesser extent, the full nodes. Now, let's talk about the processing power of the users. This graph shows that relationship. On the left side, we see how many users in the system are able to process a small amount of data. In other words, they're slow participants. All of them are able to process a small amount of data. And on the right side, we have very fast users who are able to process large amounts of data. And as we can see, for most systems, for almost virtually all populations, rather, there's a very small percentage of those users that are going to be really fast. So you can even think of just, like humans. How many humans are going to win the Olympics? A very, very tiny percentage. Or in other words, few people have a supercomputer or a data center back, in their living room. So what happens when the system gains users? Well, in this case, the red circle expands. But what happens then to the green circle? Well, if the red circle expands, that means that there are more users. If there are more users, there is more data, because those users are producing data. All of them are producing data. If there's more users, there's more data. And that means there are fewer people who can handle processing all of that data. So the green circle shrinks. Now, this is a very important circle. Just because it's small doesn't mean it's not important. In fact, this circle is kind of, at the heart of the entire block size debate. Because these are the deciders for the rest of the users. They're the ones who are making the decisions. They're the consensus participants. Let's talk about consensus capture. Let's say we have like a small town of 4 people that are in consensus with one another, and this small town is voting on what laws they want to pass. Well, they do a really great job. And so they're living their daily lives, voting on things, talking with each other, coming to agreement, doing the consensus thing. And they're doing such a great job that they attract a few extra people who want to join their town. But these extra people, not all of them are interested or are capable in being lawmakers. And so they just kind of go by the decisions that the consensus participants are making. And as time goes on, the consensus participants are brilliant. They don't really have many problems because they don't have very many users. So they get more users, and more users, and more users, until they're ruled by the 1%. So what can we do about this problem of sorts? Is it possible to get around this triangle relationship that we observe in systems, not just in blockchains, but in legislatures and governments? Well, what we can do is we can stop trying to build systems like this, where we have a group at the center that's making decisions for a whole bunch of people. And instead, we can create systems that employ multiple consensus processes that are independent of one another. And that's the critical part, is that they're independent consensus systems. So the Lightning Network is an example of another way of getting around the triangle by not using consensus. No consensus, no problem. It takes two edges of the triangle and combines them. You have one independent system, Bitcoin, on the left, and you have another one, the Lightning Network, on the right. They're both decentralized, but they focus on different things. One has consensus, the other one focuses on scale. And so here we have the Lightning Network with payments going through. And what's neat about the Lightning Network is that, you can kind of think about just like how when you send Bitcoins to an exchange, and that exchange, and I'm over time, by the way, right now, but this is also the break, so I'm lucky, fortunate. Thank you, Kurt, for adding me at the end. The exchange doesn't have a limit on the transactions per second that it can process, because it runs all of those locally. Those transactions don't touch the blockchain. But what's cool about the Lightning Network is that if the user's software notices something fishy going on, it can go to the blockchain. And for that split instant, that's where the Lightning Network interacts with the Bitcoin network. And that's where you have a little instant of consensus where the user can catch, overwrite, and penalize any naughty behavior. Now, sharding is another, well, it's not really another. We've already talked about it. This is just another name for the idea of independent consensus processes. And here, you basically take two DC systems, two decentralized consensus systems, and you link them in a clever way. And this represents a middle ground of the triangle, where you sacrifice a little bit of consensus and a little bit of decentralization to get some scale. And it kind of looks like this. And there actually aren't any blockchains out there today that do this, but there's a lot of research currently being done on this. Papers have been written about it, and this stuff is in development. But I want to leave you with a final warning, which is that as you're researching and reading up on all of these systems, on payment channel networks like Lightning, on sharding solutions, I want you to be vigilant and be aware that just because something uses the name payment channels, or just because something uses the term sharding, doesn't mean that it's going to be a decentralized system. Doesn't mean necessarily that it's going to be the same as another system that also says that it uses sharding or payment channels. Ask yourselves, are these independently operated systems, if it's a sharded system, for example? Are all of the shards actually independent of one another? Do they have some level of independence? Or is there some kind of cartel behind the scenes controlling everything? So I think that's the end of my talk. Thank you very much. Blockchain, blockchain, blockchain.